Okay, chapter 5 is about a planar kinematics of a rigid body. Okay, so we will see rigid body motion, translation, rotation, motion, instantaneous zero, and relative motion. Right. So these are the keywords that we're looking at. So later you will see a different equation that you are familiar with. You will see transition equation. You will see reference relative motion equation. Then later you will see rotating flame reference. So you will be seeing before chapter 5, you are using X and Y axis. In this chapter, you will see another reference axis that you use it to do relative motion and also rotating flame. Okay, you will see two set of X, Y, Z axis in this chapter. Okay, so have that one in mind. Okay, we'll go slowly. First, we define what is rigid body motion in a planar form. Okay, planar form here, it means that you imagine the motion will be happen on a piece of A4 paper, right? And then whether it is rotating or translating, like that, whether it's translating, which is translating means move from one location to another location. Another one is rotating. Okay, so we will see these two motion in this chapter. We'll look at three motion. Okay. So my slide is, we have three type of motion. We look at the first type, translation. So on your tutorial handouts there, you will see translation. This is a part of the translation. You have two types of translation. One is the most basic one, meaning straight line translation. Straight line translation, because the motion move in the straight line. Okay, if I use a piece of paper, translation in straight line, in other words, we can use X, Y, Z position, or rectilinear, rectangular plus linear, rectilinear transition means it move in a straight line like that. Okay, move in a straight line like that. Another one, also translation, but it move in the curvature motion. You imagine this move like that. Okay, it move like in a curve, right? In a curve, not in a straight line, like that. This one is rectilinear, and then this one move in the curve like that. This is curvilinear motion. Okay, there are two. One is a straight line that you can define in XYZ in the XYZ coordinate system, move in the straight line XYZ. This one move in the curvilinear motion. So curvilinear motion, normally you will see tangent and normal, and also the R component, right? So this chapter combine what you learned in previously, the linear motion and also curvilinear motion, right? This chapter combine what you learned previously, and then you apply in this chapter. Okay, the rest you can read. The rest you can read. So the first type is called translation. You have two types. Each type you need to use different type of equation. This one is curvilinear. Again, curvilinear, you need to see the tangent and normal direction. But this one, you can use the normal XY coordinate. Meaning, if it's a rectilinear, in the X, you can convert into vector form, which is I and J and also K. But here, because of rectilinear, you need to use the tangent and normal, and sometimes you need to use the vector form, IJK. This one you can still choose not to use IJK, but this one you should use IJK. Right, there are two types of translation. Okay. Next, rotation. Rotation, the rest you can read on the slides. Rotation is around a fixed axis. So as you can see from the diagram on your handouts, this is the rotation axis. So the plane is rotating around the body. Okay, it's rotating around the body. So when you have a rotation, you can either have anti-clockwise or clockwise direction. So this one gives you positive and negative sign later in your calculation. Same with the translation. Translation normally move to the right or x-axis is positive, moving up is positive. In here, curvilinear one, we follow the motion. Okay, we follow the motion direction. If the motion direction is in this way, so we follow the tangent direction. Tangent is positive. Normal always pointing to the center of the curve. First type of rigid body motion is translation. Second type is rotation about the fixed point. Fixed axis. Another one is called general plane motion. General plane motion is a combination from translation and rotation combined together. You get general plane motion. Okay, this is the diagram you have on your handouts. So basically, when you talk about rigid body analysis, you need to consider these three kind of possible motion. If the basic one is a translation, and then you move to rotation, you combine translation and rotation, it will give you the third type of rigid body plane motion. It's called general plane motion. Okay, so you imagine this one as a A4 paper. Okay, A4 paper. So translation like that, rotation is like that. So you combine the two, it can be straight forward plus rotation. Okay, plus rotation like that. Okay, it can be a very complex calculation when it comes to general plane motion. Okay, it can be go like this and then suddenly change to another orientation. Okay, so later we will look at each individual analysis, right? And you should be able to solve. All right. Okay. So example of rigid body motion, why we study this one in engineering dynamics, because you're having mechanical engineering. You, in your career life, you will see piston, or even in your normal life, you will see piston movement. This is piston movement. This is curvilinear translation, that the piston only can move up and down or left to right. Okay, this is called curvilinear translation. Imagine a piece of paper, your piston can only move like that. Okay, this is called translation. And again, translation have two types, curvilinear and also rectilinear and curvilinear motion. This is rectilinear translation. And then this is rotation. Circle is a rotation. This one also move in the rotation around the fixed axis here. This object, rotation. This one, rotation. Main part of the question 5, chapter 5 question will ask you to analyze this one and this one, not this one. Okay, fixed rotation, This one under static chapter or under static module, when it comes to engine dynamics, you need to calculate this part and this part. Okay, this part, it gives you general plane motion, because as this one rotate, this one go translation. This part, let me orientate my. Okay, so means this part, it go front and back. It can go front. At the same time, when it go front, this point, when it rotate to here, this object orientate using, imagine you focus on this point. When this point rotate this way, this point, this arm of this object, it will move down. So you will see there's a rotation of point here. This point, you rotate to here. The body frame, the body here, it will orientate from this angle into a straight body when this point reach here. So it's a combination between translation and rotation. Same with this one. Okay, same with this one. Because of the rotation, because of this point, rotate, this body will change orientation and also distance, either move forward or backward, depend on the rotation, the linkage of the rotation. Okay, so bear in mind, in chapter 5, you are not calculating these simple things anymore. You are looking at this linkage. Okay, you're looking at this linkage. So we look at translation. We start developing equation for translation. Then we look at rotation. After that, we combine translation and rotation equation. We get general plane equation. We start with the translation explanation first. Okay. So let's say when you want to calculate translation, there must be a movement in this sequence. So translation have two types. One is rectilinear, one is curvilinear. So let's say we assume we look at curvilinear motion, which is move in this way. Right. So when you move in this way, when you do calculation or derivation of equation, you need two reference axes. That's why on your handouts, on the screen here, you see there's a original position axis, y and x with the O. Let's say this is your principal reference axis, or we call it fixed coordinate system, meaning start from beginning, this is the one that you fix in your system. This axis doesn't change according to your object. It's fixed there. So this one become your reference or anchor point from all your calculation. For chapter 5, it's important to give reference axis, especially for fixed coordinate system. This axis will give you the remaining parameter. Okay, so first thing for chapter 5, you draw is the fixed coordinate system. X and Y, label O as your fixed coordinate system or your anchor point. Next, you need a translation reference axis, where this is the original position. When translation, it means it moves to another new position. So when the object moves to the new position, you give a new axis with y prime, x prime, or x comma, y comma. It means that this is your new position axis. And if the object is experiencing translation, we will name the axis as translating coordinate system. If it's having a rotation, then this axis, we name it rotating coordinate system. And if it combine two, we'll name this one as general plane coordinate system. Okay, so we start with translation first. Try to understand there are two different axes every time you solve chapter 5 question. One is the reference axis or primary axis, fixed coordinate system. Another one is on the object. First you draw the fixed, then the second axis you draw on the object with the prime symbol, x prime, y prime, and then label new position A, B, C, D, or any symbol, right? So this one, it means from zero, transfer, translate, moving from O to A. You put A there. Then A, there's a point B here. Okay, there's 2 points. There's a 2 point of this system. A is the anchor point for this object. B is referring to A. Okay, A and B is on the object itself. It's just that A is 1 point referring from O. So this O to A, O to B, there are 2 points. There are 2 points. So from here, in chapter 1, chapter 2, you learn about positioning. Since the beginning, we used R for the position, and this one is vector form. Vector have magnitude and direction. This is magnitude, arrow represent direction. So position from 0 to A, you label as RA. RA means position of A referring to O. What is O? It's a fixed coordinate system or your anchoring point, or we call it your primary reference system. O to A you label as RA. When you're referring from origin O to point B, we name it as RB. Arrow must be correctly pointed. 0 to A, 0 to B. And then this one form a vector triangular. This one form a vector triangular. When you want to read A to B, when you write R sub B stroke A, when you write R B stroke A, what does it mean? It means B referring to A, meaning if you write this way, B stroke A, it means you're looking from A. B stroke A, it means you're looking from A look B. This is how I remember. And if you wrongly write this notation, means you're calculating the different thing already. R sub A stroke B is different from R B stroke A. I mean, if you flip these two, A and B, flip position, it means different thing already. R B stroke A, it means the last one is A, right? You stand here. You stand at A, look at B. Yeah, this is how you write. You write the wrong one means you calculate the wrong thing already. Because this is a vector, vector 0 to A, you get RA. Vector RB is from 0 to B. Vector A to B is RB stroke A. It forms a vector. Which one is the resultant in the vector triangular? This one, right? This is a resultant vector, right? Vector 1 plus vector 2 equal to the resultant. This is how you develop the vector triangular. So when you write the equation for vector triangular, what can you write? RB equal RA plus R sub B stroke A. I repeat, all the arrow here is a vector. Recall your understanding in vector triangular. You look at the arrow, how you form a triangular beginning to the end point consists of two vectors, RA plus this arrow. This arrow is RB stroke A. This is the resultant. How you draw the resultant? You draw from the beginning until the last end. This is your resultant. So when you draw the triangular, you can write the relationship between the three vectors. In this case, this is the resultant. So RB equal to the summation of RA plus this arrow. This arrow is RB stroke A. Okay, so this basically form the foundation for translation equation. You're using this triangular equation, RA, RB, RB stroke A. This is position. From position, you should know how to derive from a position into velocity, from velocity into acceleration. This one you learn in chapter 2 when you learn about the graph, right? ST graph, VT graph, AT graph. So this one is the application of what you learned in the previous chapter. How you change the position into velocity, you take the derivation over time. You take position divided by time, you get velocity. You differentiate one more time, you get acceleration. Okay, that is the whole concept of this chapter. If you understand what I speak just now, what I say just now, from position to acceleration, if you understand that, you should be no problem solving question chapter 5. We will keep repeating this concept. Okay, if you understand this diagram, you understand the vector form, because the question was still the same. Ask you to draw free body diagram, ask you to draw the RA, RB stroke A, calculate the velocity, either one is missing. After that, find acceleration, either one is missing, find the acceleration, and so on. Okay, so basically, we will keep repeating the same thing for chapter 5. So first position, as what I say just now, RARB position. Yeah, so I mentioned already. The name for this vector is called relative position. It's relative position. So it depending how you write, B stroke A, it means you are looking from A. Position of B with respect to A, or in the layman term, means you're looking from A, that object referring to A. R of B with respect to A. But in this module, I will just read out the formula rather than I just keeping saying this one. Okay, then I already explained how to get this vector addition. I already explained about the triangular just now. We have this formula. From this formula, position, derived by time, divide by t, divided by t, divided by t, you get velocity. Once you get the velocity, you divide the velocity equation with the time, you get acceleration. Later, we will go through a few slides deriving this section, this one, because this is a bit more complex mathematically. So later, we will spend a little bit more time on deriving this component. Okay, or call it relative position component. Okay, so far I think everyone is everything on the screen here is quite clear for you. Okay, first equation for today. I think you've seen this one so many times already. This is a vector equation. We'll move on. After position, we talk about velocity. Right? So from here, how to change position to velocity? You take position divided by time, or taking time derivatives. So this one divided by t, divided by t, divided by t. This one become velocity B. This one velocity A. This one become relative velocity of B from A. the RB stroke A, you're going to find this one, expand this one into coordinate x, y, z. Okay, so far here to here, I think everyone's still okay. Now, okay, just a side note. VA, VB, here there's a name for them. In textbook or in a tutorial question later, it will ask you to solve something. So if it asks you to solve the main velocity, VA or VB, you will see that you need to solve absolute velocity of something. Okay, absolute velocity, they are measured with respect to x and y axis. They are measured from the fixed coordinate system. Okay, velocity A, velocity B, and they are absolute velocity because they measure from the primary axis here, or fixed coordinate system. Yeah? Okay, so this one you measure from fixed, this one you measure from fixed. However, this one is a relative position. Where is the base of this one? The base of this one is on y prime, x prime axis, or we call it translating coordinate system. So don't mix between this one, and this one. These two, you refer to primary or fixed coordinate system, x and y. However, this one, you're referring to translating coordinate system. So don't mix up this one and these two. These two is easy to find. However, the challenging part is this one, because you need to be sure of the translating coordinate system. Okay, so I'm going to explain why this one becomes 0. Since the magnitude of RAB is constant, this one is constant. This one, A to B position, is always constant. Not always, but in this case, A and B distance on the blue body here is fixed. A to B or B to A. But in this case, it's R, B stroke A, means if you stand here, if you stand at A, you watch B, the distance that you watch always same. Correct? Means relative position. If you stand here, look at B, always same. And R is constant. When you take time derivative, meaning if you take this position divided by time, does it change? If you divide by time with a constant, you get 0. Means you divide by time means the rate of change of that parameter. This one doesn't change. So if you do time derivation with a constant value, you get 0. Meaning, for example, dy dx. If your x is a constant value, dy dx equal to 0. Or your y is a constant. Y is a constant, dy dx equal 0. Okay? That's why we can cancel or put as 0. When your A and B doesn't move, A and B distance is the same throughout the problem or throughout the analysis. Okay. And another, because of direction R stroke B also constant. Okay, magnitude same, because this is a vector. Vector magnitude is the same, direction also same, so it doesn't change anything. So when you do derivative over time, it becomes 0. So it gives you this velocity equation. It gives you VA equal VB. Under one scenario, your A and B fixed point, it doesn't move. Only you can use this equation. So from position, you derive the equation for velocity. In this case, your A and B are fixed constant. and it gives you RB equal to RA. Again, where do you measure these two velocity? You measure from fixed coordinate system or the primary reference system. These two is primary reference system. This component is referring to translating axis, y prime and x prime. They are different system. AB, VA, VB, VA are from the same system, from same axis, but this one is different axis compared to the previous one. Okay, so we have arrived at the second equation. First equation is this one. Second equation is this one. What about acceleration? Acceleration, same. Take time derivative of this one and this one divided by t. You get AB plus AA. Okay, so for translation, you arrive at this equation, and this equation. Okay, write this one in your tutorial. And now position, you should write this one, velocity, this one, acceleration, this one, for translation. Okay, we have complete explaining about translation. Let's talk about rotation. After rotation, we have a short break. I believe you have this diagram in your tutorial handouts. I try to put in my full slides. This is the maximum size I can go. Although some of the wording here is small, but I think you can follow along as I explain. In your tutorial handout, you can see the full diagram. Okay, when we talk about rotation about fixed axis, you must know where is the axis. Usually through the center of the rotation. Okay, there must be a center for it to turn, right? So go and look ahead, look for the rotation axis first before you solve for rotation problem. Look for the center of the axis. So on this diagram, let's say we have one body rotating on this plane here. And then we find the center of the body. We label as O. Let's say we only look at this plate here, round plate here. So this round plate had a center O. This line is center of your rotation axis. We are now at a fixed axis. We now have a fixed axis. So this is fixed axis, rotation fixed already. And on the plate, this one, you have one position or one particle's position. We label as P. Okay, we label as P. How do you identify or how do you define position of P? You label as R. You are using the R to define the P point position from 0. O to P point is the distance or the position for P. You use R. Okay. And when you talk about rotation, there's a direction, right? Either clockwise or anti-clockwise. How do we fix? Because if you don't fix, it's very hard to, when you calculate later, positive, negative, you don't know what direction is spin. All right. So we must fix one general direction for our rotation. Same like what you define for X and Y direction. Moving to the right, always positive. Moving up, positive. And moving along Z axis, always positive. That is translation. When it comes to rotation, we will use your hand, right hand rules. Okay, use your right hand rules. What is your right hand tell you? What is the positive direction of rotation? What is your finger tell you? Is a anti-clockwise direction positive. So for rotation, we use right hand rules as our tools. So every time you start solving for rotation, you look at your right hand. Your finger will tell you the answer. Huh? So rotation is following your finger. So this is anti-clockwise. So when you talk about rotation, you talk about angle. So there must be a starting point for rotation. So if you go back to the origin O here, there's a line here. There's a reference of angle. You start from this line, and if you measure from this point to the point P rotation, you follow your finger is anti-clockwise direction from one reference point to P. This is positive angle we label as theta. Again, how to define positive direction? Look at your right hand finger. Curve in anti-clockwise. So positive direction is from one point anti-clockwise to the position of P. Okay. Later we'll talk about the changing of a small angle here from P to a certain angle. That's later. This one later. Huh? But at least you know what is the theta mean. What is the rotation angle mean. Huh? Okay. Other than your right hand, this is right hand rules. We call it right hand rules. So your right hand will tell you something else. Beside the rotation direction, what is the what we call the thumb? The thumb tell you. The thumb will tell you the axis of positive fixed angle, fixed axis. When you rotate anti-clockwise, the positive is going up. When you have rotation anti-clockwise, you follow the angle of rotation. The thumb will tell you the positive direction of your fixed axis. Okay, later we look at omega, we look at alpha, and del theta. Okay, del theta means the changes of angle of rotation. In static, you learn about omega, touching a little bit on alpha. Omega is the rotation, the rate of changes of your rotation. Alpha is the acceleration, angular acceleration. Omega is angular velocity. Try to recall back. This one you learned in your static one. Now you apply in engineering dynamics. Okay. So I explained about the diagram already. We'll go into mathematics derivation. The rest you can read. I already explained all these points. So angular motion. Since a point is without dimension, it cannot have angular motion. I highlight this one. Only lines or body undergo angular motion. Okay, apologize for the thunder that we experienced in the campus. Just now, I think there's some spike in the signal there. Right, let's hope every one of you is okay on your side. Right. All of you able to hear me? The audio is okay? Audio okay?
Yes.
Right. So again, in chapter 5, we are no longer talk about point. When we talk about angular rotation, we are not looking at point, but we look at lines and body. Then only you can use equation for angular motion. Meaning this omega, alpha, and this change of angle here or right hand rules, this one only works for body and lines. That's why chapter 5, we call it a rigid body motion. Okay. All right. So the rest I I explained already, the R, angular position, okay. This angle here is called angular position. So you will see this wording during the question or during the tutorial question. It asks you to find something. So if you ask you to find the angle theta, it means angular position. So you ask you to find angular position of certain after a certain time, after 2 seconds, 3 seconds. What is the angular position? It means find the theta here. Okay. And then this one, angular position, is from fixed reference line to R. From fixed reference line to R. So this is fixed reference line to R. This is the R. Okay. Theta. And small changes, we call it displacement. Okay. Small changes called displacement. Okay. Small changes called displacement. So d theta is angular displacement. So again, this also is a vector. Vector had magnitude and direction. So when you do d theta, it is the magnitude. What is the direction? Follow your right hand. Okay, direction, you follow your right hand rules. It can be degree, radian, and revolution. Okay, 1 revolution equal how many degree? 360. 360, how many radian? 2 radian, 2 pi radian. Okay, so sometimes it convert from here to there. Okay, anyone have question? I have seen somebody turn on your mic. Okay, if you have question, just ask. If no question, you can mute your mic. Okay, so this just things that you learn in your statics. 1 revolution equal to 2 radian, 2 pi radian. Direction followed by right hand motion. The rest is what I explained already. Angular displacement, they are counterclockwise, follow your right hand. Angular velocity, angular velocity is your omega. Is angular velocity, it gives omega, which is your theta. You use your displacement divided by time, which is theta naught. Theta with a naught or theta divided by time, it becomes omega. It becomes this one. So if you take your omega divided by time, it becomes angular acceleration. It becomes alpha. Okay, so this is just a side note. You learned this one before already. Omega equal to displacement divided by time. In here, rotation, our displacement is angle theta here divided by time. Or sometimes in short, we will just write theta dot. On top of that is dot. There's a dot here, theta dot, if you write in the shorthand. In the unit of radian per second. Okay, this omega is a vector. Vector have magnitude and direction also. This is how you calculate the magnitude. You differentiate with time, you get the magnitude in radian per second. How do you find the direction? Ask your right hand. Right hand rules. Angular velocity acceleration also same. We use the alpha by time differentiation of this one. Again, you get alpha. Or if you want to use the displacement, you just displacement, you have double differentiation over time, you get angular acceleration. Okay, so this one you learned before, right? In statics, and also if you convert the same concept from displacement, it's still the same, only change the symbol. Something you need to take care is that if you have increased in angle. Increase in angle, we call it acceleration. If you slow down, if your omega slow down, then you have angular deceleration. Angular deceleration or deceleration. Deceleration. Huh? So means you slow down. If your omega slow down, you have alpha as negative value or have a smaller value compared to the previous one. Huh? Then you can rewrite these two into this form. Okay. Okay, we have a short break. We stop at angular velocity and acceleration. We will come back after the short break. Huh? Let me stop the recording.